Hello, Orbital fans. This is Dongwook again. Welcome to the third part of the tutorial. And on third part, we're going to look at first the interaction between orbital angular momentum and magnetization. And this is really important direction, in my opinion, because what makes orbitronics really important in solid state physics or condensed matter physics is that um, orbital angular momentum and orbital currents are not independent as they are, but rather they interact with many orders and excitations. And study of orders and excitations is really one of the central themes of condensed matter physics, and also manipulation of them can sometimes directly lead to device applications. So I want to introduce you two very important concepts, orbital torque and orbital pumping, which are reciprocal to each other, that results from the interaction between orbital angular momentum and local magnetic moments. But to begin with, let's review important concepts in spintronics. Magnetization dynamics is often described by Landau-Lifshitz-Gilbert equation. The first term describes the precession with respect to the effective magnetic field, including the internal field like anisotropy, and the second term describes the damping due to dissipation, coupling with other degrees of freedom. And the third term is the one that describes the torque that is externally applied by magnetic field or by injecting spin or orbital angular momentum. And generally, the torques have two terms. Generally, we call it field-like and damping-like torque terms because the field-like torque acts as if there is an effective magnetic field in the direction of S. So that's why it's field-like. And the damping-like torque is called damping-like because it's applied in the same or in the opposite direction to the direction of Gilbert damping. So sometimes, depending on the context, it's also called anti-damping when the torque compensates the Gilbert damping term. So anyway, these two terms can be separately measured in experiments and can be easily distinguished because they have different symmetries with respect to the reversal of the magnetization direction. And so the question is how we generate torques. One prominent mechanism that is known is spin transfer torque. And the main idea is following. So you first prepare electrons with finite spin polarization, and the incident electron will then penetrate through a ferromagnet. And after the interaction with the ferromagnet, an outgoing electron that will have the spin in the same direction of the spin of the ferromagnet. So therefore, if you consider the boundary condition for the initial and the final process here, you see that the direction of the spin has changed. So therefore, as a result of the action and back action principle that is coming from the conservation of angular momentum, the direction of the macro spin should also rotate in the opposite direction to the rotation of spin of electrons. And this is the direct consequence of the conservation of angular momentum. And I want to emphasize that in principle, the magnetic dynamics is governed by the conservation of total angular momentum, including both orbital and spin parts. For historic reasons, however, orbital part didn't get enough attention that it deserves, unfortunately. So that's actually what we're going to focus on. But there's another important development that we have to know before we discuss orbital torque, and that is spin orbit torque. This really revolutionized spin orbit torque after its discovery around 2010. And it really proposed a way to efficiently generate spin current by using spin orbit coupling of heavy metal like tantalum here, and for example, by using spin Hall effect of tantalum in this experiment, the authors have demonstrated that magnetic order can even be switched. Similarly, also by using both spin Hall and also Edstein effect at platinum cobalt interface, the perpendicularly polarized magnetized system can also be switched. And in the past decades, actually, there were really a lot of debates on the microscopic origins of the torques. In my opinion, that is still going on. So let me ask the following question. How do we systematically classify mechanisms based on the physical microscopic processes? That is, somehow spin and orbital angular momenta are involved, but how? And how angular momenta are exchanged between different degrees. And this is the questions that I like to answer. And I want to emphasize in this tutorial that orbital angular momentum is so crucial in the microscopic process. By the way, on spin-orbit torque in general, it's really important concept and then important also for applications. So I would recommend these review articles and the roadmap if you want to know more about. But to really approach this problem more generally, let's take a look at where angular momenta are stored in solid state system and how they are exchanged. And this is, in my opinion, one of the most general approaches that you can take. So that is the total angular momentum of an entire system is conserved. So therefore, we should understand these microscopic processes in terms of transfer or exchange of angular momentum rather than the generation or loss of angular momentum. For solid state system with electrons, generally we often have the following degrees of freedom. That is orbital and spin part of electrons, which are coupled by spin-orbit interaction or spin-orbit coupling. And then these interact with local magnetic moment by exchange interaction here between the spin and local moment, and then between orbital and lattice by crystal field potential. So therefore, if we start from an effective single particle Hamiltonian, such as the Kuhn-Sham Hamiltonian in the DFT, we can start from the following general term, that is CF is the crystal field potential generated by the crystal ions and the rest of electrons, and the spin-orbit coupling between L and S, and the exchange interaction. So individually, they all describe these interaction channels that I show here. So in this work, we have derived the continuity equations for the orbital angular momentum L and the spin angular momentum S. And as you notice, this is not just ordinary continuity equation because L and S, they are individually not conserved. Actually, it's the same for J, L plus S, they are not conserved. It's because of all these interaction channels and angular momentum is exchanged between all these degrees of freedom. And anyway, individual terms appearing in these equations is that the first one is orbital current, the product between the velocity and angular momentum. And we have spin current here. This is the spin flux. And then we have crystal field torque. So generally the form is quite complicated. We don't know V before we specify a crystal symmetric system, but generally can be calculated as a commutator between L and potential. And also we can compute so-called exchange torque between the spin and local magnetic moment in this way. And this is given by M cross S. And this is the torque that acts on the magnetic moment and that contributes to, for example, switching of magnetization. So I want to emphasize this point. And finally, we have so-called a spin orbital torque or spin orbit torque that is coming from the mutual precession between L and S. And this describes the conversion of angular momentum between spin and orbital angular momenta. So now we basically have all the ingredients. And the question is how we classify microscopic mechanisms and then understand them. So to do that, let's look at the steady state condition for the spin. So in the steady state, the time derivative of the spin should be zero because everything should be stationary in DC. So we have the following constraint. And now, when you look at the torque acting on local magnetic moment, and that is mostly relevant in magnetic systems, and then torque on magnetization is the minus of the exchange torque. So therefore, from the equation above, we get the relation that torque on M is given by first influx of spin angular momentum and second spin orbital torque. So therefore, if we consider first the case with without spin orbit interaction, the entire torque on M is given by spin current influx. And this is exactly the regime where spin transfer torque acts. So it means influx of spin equals the torque on magnetization. And you can also consider the opposite case without spin current. For example, without any flow, we can have spin accumulation and orbital accumulation. And in this case, the entire torque is coming from the spin orbital torque, L cross S. And historically, so far, the first term used to be called spin transfer mechanism or spin mechanism, and the second term used to be called or spin accumulation or interfacial contribution with many different names actually, inverse spin Galvani effect, etc., etc. But then let me ask you a question. Where where is the orbital angular momentum here? So, and here comes the orbital angular momentum, okay? First, in the spin current here, spin current could be coming directly from externally, but spin current could actually be converted from orbital current, as we have discussed in part 2 of the tutorial. And I would like to call this first type of orbital torque because fundamentally this is not so different from spin transfer torque, but just that the spin current is prepared from orbital current. In the second regime, we can figure out that first, if there's orbital accumulation, then there will be torque on M. Also, when there's spin accumulation, there will be torque on M. So it seems like it's quite confusing, but I will come to the point later that actually the spin accumulation picture and orbital accumulation picture in this type of type 2 mechanism are equivalent, actually equivalent picture. Just a different way of looking at it. So type 1 orbital torque, the mechanism was proposed in this theoretical paper. And what we have proposed is that we can prepare spin current when there is spin-orbit coupling, and then orbital current can be converted into spin current in this way. So eventually, when there's exchange interaction, and the spin angular momentum can be observed. So this is actually quite similar to spin transfer torque. But this can be detected, for example, in this work. It was shown that actually the direct spin Hall torque contribution in the ferromagnet can compete with the contribution coming from the orbital channel and being converted to spin. And sometimes, depending on the combination of materials, actually they can have the opposite signs, and you can actually focus on the sign change of the torque by carefully paying attention to it. And another very important realization is that actually this conversion doesn't necessarily have to take place for a given single material. For example, in these two works, they got a clever idea for inserting platinum layer with large spin-orbit interaction to efficiently convert the orbital angular momentum into spin angular momentum. And therefore, they could efficiently enhance the efficiency or change the sign of the torque eventually in these two works. But later, actually, we learned that there is another contribution to the torque, orbital torque, with where the property is quite different. So a type 2 orbital torque, I mentioned that I refer to the following term, L cross S torque, due to the exchange of angular momentum between spin and orbital part. But now, let's look at the induced component in non-equilibrium. So in induced setup, we have two contributions. The first coming from induced angular momentum L, and second coming from induced spin S. But in equilibrium, L is close to 0 due to orbital quenching. So therefore, the second term can be neglected. So eventually, when we take the ground state value of S and non-equilibrium value of delta L, we get the following expression. That is, torque acting on the magnetization is given by delta L cross M, meaning that M and delta L are going to mutually precess each other. So to summarize, type 2 orbital torque is directly coming from orbital accumulation, not the orbital current. But then when there's exchange coupling together with spin-orbit interaction, this delta L can have effective field on magnetization. And then what about the physical picture that we had on the interfacial spin accumulation picture? So I want to emphasize that ultimately, fundamentally, the torque acting on M is coming from spin accumulation. That is due to exchange torque. This is correct picture. But however, in the steady state condition, if assuming that we have only this one exchange torque together with spin orbital torque, these two equations should be identical. So therefore, we come to a conclusion that the induced spin and induced orbital angular momentum are related in the following way. So therefore, you can understand the torque either in terms of spin accumulation, coupling to M by exchange interaction, or either by orbital accumulation, coupling to M through spin-orbit interaction. And these two are describing exactly the same physical situations, but simply looked from two different angles. And type 2 orbital torque is also it's quite interesting because it's coming from directly orbital accumulation. So therefore, this depends really sensitively on the orbital texture and the orbital dependent band splitting. So this is quite K dependent. For example, locally in cubic systems, the orbitals are split like this between T2G orbitals and EG orbitals. But when we start to consider the kinetic energy of the electron, then for example, in this case, T2G manifold will have additional splitting between YZ and the ZX and XY and ZX orbitals. And the splitting is simply coming from the kinetic anisotropy or the anisotropy of hopping parameters. For example, YZ orbital along X direction has much weaker hopping compared to the other because of the small overlap of wave functions through conjugated pi orbitals. And this structure depends on the direction of momentum and the direction of the hopping. So therefore, for electrons along x direction, kx direction, then hybridization between x, y, and zx orbital can become really efficient because two levels are almost degenerate. And we call this hotspot for Lx. On the other hand, for Ly component, xy, and then yz orbital can hybridize efficiently. So, so hotspots for different components of angular momentum depend on a lot on different zones of angular momentum. And this is the notion that we call orbital hotspots. And it has really important implications. The first thing is that on hotspots, non-equilibrium orbital angular momentum through coherent superposition can become really efficient because of almost resonant hybridization between the two is possible because of degeneracy. And the second, because electrons are so much confined in K space, there's not so much destructive interference of different Bloch vectors K. And actually for spin, usually in ferromagnets, this destructive interference of all the Fermi electrons will lead to a very short decay lengths of spin. But for orbital, because it's governed by the hotspot electrons in small zone in K space, this dephasing is quite prevented. So therefore, we, with my colleagues, we have predicted that orbital angular momentum can go really far without much oscillation because of hotspot, while the spin is actually showing oscillating decay behavior. And so therefore, one of the key tests that we have proposed is that type 2 orbital torque will show a quite slow saturation behavior with respect to the thickness of a ferromagnet. For example, in this work, with Hayashi and others, they have shown that the torque efficiency of nickel titanium bilayer gradually increases with respect to the thickness of nickel. So this is quite clear indication that the length scale for the torque is somewhat far beyond the spin dephasing length. And also by comparing the torque contribution from pure nickel, it shows that actually the self-torque contribution is the opposite to what was observed here. By the way, also similar findings in experiments were also published in the following works. So please pay attention also to many other deep works listed here. So to summarize so far on the orbital torque, type 1 orbital torque is coming from the orbital to spin current conversion. And this conversion can take place in a ferromagnet, but it can also take place in another material like platinum. So this is quite a nice way to physically separate two different microscopic processes for generating the spin. First generating the orbital efficiently, and then convert orbital to spin more efficiently. And type 2 mechanism is coming from hotspot electrons and orbital accumulation directly. And because it's coming from orbital accumulation, crystal structure and orbital texture are very crucial in its mechanism. So therefore, depending on the crystal structure and the symmetry, you can actually control type 2 orbital torque. This was actually one idea that was presented in this paper that we presented in 2024. So, so far we discussed orbital torque, but regardless of type 1 or type 2, in both cases, spin-orbit coupling in ferromagnets is still a very important factor. And the reason is that orbital angular momentum has to couple to magnetization through spin-orbit coupling fundamentally. So let me briefly look at the band structure effect of the spin-orbit coupling in ferromagnets. For example, here I have taken an example of iron BCC phase, and I show the band structure. And in color, I show the spin polarization of each band, and also correlation between L and S for individual states. So let's first look at this plot. First, we see exchange splitting here. That is about 2 electron volt for iron. At the same time, we also see T2G orbital EG band. This is the 10DQ for the crystal field splitting. And we also have another T2G band here, which is exchange split. And EG minority band is somewhere far above here. And on the right, LS correlation is shown. But what you see is that for iron, actually spin orbit effect is not so much pronounced. Well, there are some hotspots here, 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 or here. But anyway, overall, L.S is quite suppressed in many points in the band. But when we look at similar band structure in FCC nickel, here I show along KX line, and then we first see that in nickel, exchange interaction is much smaller. It's about 0.6 or 7 electron volt, much smaller. But at the same time, crystal field splitting, that is T2G EG splitting, is bigger than exchange interaction in this case. And this makes nickel really interesting because of this very similar energy scale between the exchange splitting and the crystal field splitting makes orbitals efficiently hybridize. And also spins can also efficiently mix. So therefore, when we look at LS correlation on the band structure, you see on many points in the band structure, LS correlation is quite pronounced, not just on hotspot here, but also generally in many K points. So it means that nickel will generally have more susceptible to orbital injection when it comes to orbital torque. So this principle was proposed, for example, in this paper, Nature Communications 2021, and also completed more quantitatively in recent archive that I contributed. Okay, so far, we discussed orbital torque. Then now I want to discuss the reciprocal process, that is generation of angular momentum by magnetic dynamics. But before going there, let me briefly review the fundamental aspect of Onsager's reciprocal relation. Onsager's reciprocal relation is really profound that links the reciprocity in dissipative transport as well. But fundamentally, this is because microscopic dynamics is time reversible. That is, the Schrödinger equation is also a valid equation in time reversed way if we reverse the state. And this has very strong implications in linear response theory. In linear response theory, for example, we start from unperturbed Hamiltonian and apply perturbation by force A on A and force B on B. And generally, the response of A and B are written in this way, in a linear response way. And this chi AB, BA describe cross-coupled responses between A and B. But according to the linear response theory, the hallmark is that macroscopic response in non-equilibrium is given by microscopic correlation in equilibrium. And that's where actually the reversibility of microscopic dynamics enters. So therefore, if we use the reversibility of the microscopic correlation, this can also be computed for a system with time reversal. So it means that we calculate this correlation in this system, original system, we calculate the other correlation here, B and A, in the system with the opposite direction of magnetization. And then this epsilon A and epsilon B are time reversal parities of the operators A and B. For example, for spin or orbital angular momentum, it's -1. For position, it's +1. But then if we translate time, then we get the following way. So therefore, at the end, we get the reciprocal relation. That is, the response functions in the origin system is related to the response function of the reciprocal setup for the time reverse system. And then sign in front depends on the time reversal parities of A and B operators. And this has really strong implications that it's a really powerful way to think that once you can think about one effect, it means that you can also predict another pair effect that we simply call Onsager's counterpart. So orbital torque and orbital pumping are related by the Onsager's reciprocity. So orbital torque means we generate torque and magnetic dynamics by orbital angular momentum. And by orbital pumping, it means that we start from magnetic dynamics and or exert torque on magnetic moment, and it can generate orbital angular momentum. So in orbital torque, the perturbation is basically orbital-dependent chemical potential, which is coming from, for example, orbital injection by orbital Hall effect or Einstein effect. And the response is the torque on the magnetization, this one, that is exchange torque. On the other hand, orbital pumping, the perturbation is time-dependent change of the exchange potential. And following the mass, we can show that the response is generation of angular momentum, partial L. That is, L is continuously generated over time. And according to the Onsager's reciprocal relation, one can show that actually these two coefficients in linear response in orbital torque and orbital pumping are related. So, sorry. So the orbital pumping can be predicted. And it was predicted actually several years ago. And now there are theoretical papers are published. And around the time, then orbital torque pumping was experimentally shown. For example, in this work, in my opinion, it's one of the most direct observations of orbital pumping. That is first using ferromagnetic resonance, and it pumped orbital angular momentum, and generated orbital angular momentum was measured via the inverse orbital Hall effect in titanium in this example. And also similar experiment was also done by using the spin Seebeck effect, or can be orbital Seebeck effect. It means that incoherent magnetic excitations can also pump orbital angular momentum, and the conversion to charge current was detected in this LAO-STO interface in 2D. And similar experiments were also done, especially works by Azevedo and by Gambardella. And interestingly, also pumping can also take place in ultra-fast timescale by using femtosecond laser. So by femtosecond laser with ultra-fast heating, then it can also generate angular momentum, and the emission of angular momentum, generation of angular momentum in ultra-fast timescale was detected by the emission of the charge current that is generated by inverse orbital Hall effect or inverse orbital Einstein effect. And similar experiments were also reported in many other groups, especially in these following works around the same year. So it really, I think, opens the direction that orbital angular momentum can do many things in coupling with magnetic order, with light, and probably with many other orders and parameters in solid state. So I think there are many still possibilities that you can still explore. So to summarize, we look at hyperorbital torque coming from spin injection, but the spin is prepared from orbital to spin current conversion. And type 2 orbital torque is coming from direct orbital accumulation, and it gives rise to effective spin-orbit field on M. And this is sensitive to orbital texture and crystal symmetry. And again, I want to emphasize that this picture is actually identical to the picture based on the spin accumulation picture. And finally, we look at the reciprocal relation between orbital pumping and orbital torque. And this implies that magnetic dynamics can lead to non-equilibrium orbital angular momentum, which is now called orbital pumping. So this is the end of the third part of the tutorial. And thanks a lot for paying attention to all the tutorials if you have done. And if you have any questions further, please approach me at any time or write me an email or any message in social media forum. Yeah, thanks a lot, and I hope all the best for you. And yeah, see you around. Bye bye.